Hello everyone, and this is Low Budget Physics. So I'm a college student. I just ended my physics class. It's Physics 209 at City College. And so I decided to make several videos on some of the topics that I understood the most, but I feel like there is not enough information online. And so today's topic is going to be Young's double slit experiment. And so there are two parts to Young's double slit experiment. There's interference, and there's diffraction. In this video, we're going to discuss double slit interference. Okay. So what Young did was that he set up an experiment which involved a natural light source. Then he had a first wall with a slit in the middle. Then he had another one with two slits. And then he had a screen which would record the light intensity. Okay. So what happened? So we have a natural source of light, which creates all sorts of light beams. And so what the first slit does, it takes the natural light and then it creates a coherent beam. So all the light that comes out from here is coherent. When the coherent beam comes to the second wall, now we have two slits. So each of the slits is going to create its own coherent light. And so those two lights, they interact with each other. And let's look at this. So we could have one coming out from the upper slit, and then one coming out from the lower slit. And so, depending on their position, they're going to have a phase difference. Sometimes the phase difference, which we will define as delta phi, is going to increase the amplitude, and sometimes it's going to decrease it. And so, depending on the position, we are going to get different light intensities. And so, what he recorded on the screen was as follows. He recorded a lot of intensity in the middle. Then he recorded a gap, two gaps from top and bottom. Then he recorded a lot of intensity again, and again, and again. So we get a zebra. We get spots where there is a lot of intensity. We get spots where there's a few intensity. Let's graph it. So this will be our y position. We'll call this y-axis. This is y. So here, this is 0. That's in the middle. So there's a lot of intensity in the middle. And then it decreases. Then there are spots when there is no intensity at all. Then it goes back to the original, and it goes back to 0. And the pattern repeats over and over and over. Now we need to describe this pattern. Let me redraw this part of the picture. So we have two slits that create coherent beams of light. Then we have a screen. So let's choose a point on the screen. Let me make it bigger, just for you. Let's say this is point P. And the first slit is going to be A, point A, and the second one is going to be point B. And so there's one light source coming from there's one light coming from the first slit, from the slit A, and then there's another one coming from slit B. And let's say this is the middle. This will be angle theta. The whole distance will be distance large d, and the distance between the two slits is going to be lowercase d. Okay, so how do we describe the intensity that comes at the point B? First, we need to figure out the phase shift of those two beams at this specific point. We are going to say that this distance, uppercase D, is much larger than the lowercase d. So basically, the distance between the two slits, it's very small. It's less than a centimeter, definitely. And this distance could be really large. This could be like 1, 2, or 3, or even 5 meters. So how do we find the difference in path of light that is coming from A and the light is coming from B? Well, we need to draw a perpendicular. And then we can see that this distance from, let me call this H, from HP to AP is approximately the same. So the difference, the phase difference, is the distance from B to H. And so in this path difference BH is going to equal to d sine theta. You will need to do some geometry here, but if you approximate all the angles, you'll get this result. You'll get that the delta path difference is d sine theta. Okay. Now, by the same token, if this is d, and the length from the middle, from O to P, is y, then as you can see from here, tangent of theta equals to y over d. But if theta is really small, then tangent approximately equals to the sine. The phase difference, the path difference approximately equals to d y over d. So if you want to find y equals capital D over lowercase d times the delta phi. We know that if we want to find the maximum intensity, the phase difference has to be an integer multiple of the wavelength of the light. So delta phi has to equal to m lambda. It will give us the maximum. And it's going to be minimum if it's in the form m plus 1/2 the lambda, where m is the integers 0, 1, 2, 3, and so on. So from here we know that we can plug it back there, and we will get the positions of y, where the intensity will be at maximum and where it will be at minimum. And this, ladies and gentlemen, concludes the interference part of double slit experiment done by Young.